In this short video, we'll look at the principles of operation of pneumatic pressure transmitters and converters. We start with a flapper and nozzle arrangement. We have an air supply that moves through a restrictor and into a chamber. You can see that air can escape out of the nozzle, and we're reading pressure out of that chamber on a pressure gauge. You'll notice the gap between the flapper and the nozzle will determine what pressure is in the chamber. If we reduce that gap, the pressure will rise as we restrict air coming out of the nozzle. Let's have a look at how this works with our pneumatic relay. We have the nozzle at the top right with an air supply coming in with a restrictor that allows air to go into the chamber that then allows air to flow out of the nozzle. We have a control relay and an exhaust port. So something you'll notice with all pneumatic instruments is that there is air constantly leaking out of these. They'll either be through the nozzle or through the exhaust port. We also have an output. Let's look at how this works now. Air moves through the restrictor into the chamber and out through the nozzle. Now, the restriction that's placed on the nozzle will determine what pressure is in the chamber that will press on this diaphragm. The diaphragm will then move to the left if the pressure builds up, or to the right if it decreases. What's moving with the control relay is allowing air to go past the control relay and through to the output. So think if we block the nozzle off, build pressure up in the chamber, we move the control relay to the left, that allows more airflow through to the output, giving us a higher output pressure. Let's see how this applies in a pneumatic force balanced instrument. We have our air supply, have our control relay just without the details, and the air is moving through a restrictor through to the flapper and nozzle. We have our force bar. So this is the moving part that is also connected to the flapper and nozzle, and the area where the force from a primary element is applied. It pivots on a point here. So as force is generated on the force beam from the primary element, the flapper moves closer to the nozzle as the force beam pivots on that diaphragm seal or on that pivot point. As the pressure in the relay chamber increases, the output signal also increases. But you'll notice this also pressurizes the feedback bellows, which applies a balancing force via the range bar, which pivots on the range wheel. This holds the flapper at a distance away from, or pulls it away from the nozzle until we reach a point of a balanced condition as it results in an equilibrium of forces. The range wheel adjusts the pivot position of the range bar as it acts in opposition to the force bar. Now, if we were to move the range wheel down, this would result in greater movement of the flapper for a given signal pressure that's coming from the relay and into the bellows. So this decreases the range of the transmitter as less input or process pressure would be required to reach equilibrium. Conversely, if we move the range wheel in the other direction, up, it would result in less movement of the flapper for a given signal pressure. So this would increase the range of the transmitter as more input or process pressure would be required to reach equilibrium. We also have the zero adjustment screw, which preloads the range bar with a force that acts in opposition to the force generated by the bellows. So when turned clockwise, the bellows are compressed and the flapper moves closer to the nozzle, requiring greater pressure to the bellows to reach equilibrium. So I hope that's helped you to see the principle of operation of a pneumatic pressure transmitter and converter, from the flapper and nozzle to its effect on the control relay and their application in a pneumatic force balanced instrument.